Hello, everyone, and welcome. Welcome for having got into here despite all the rigors of modern computing, building management, etc. This is an event of the BCS London branches, 3 of them anyway, North, South, and Central branches. You know that, I guess, because you come here to see a super event on quantum computing. So we used to talk about moving at the speed of light. Now we realize the inadequacies of that. We're going to have to start moving and thinking at the speed of quantum. And, well, there are a number of things we'll talk about in terms of quantum, because our quantum, or the London branches that I've described, North, South, and Central, our quantum lead is Kate, who has a very illustrious set of titles and things in terms of quantum, because she is a leading, more than that, you're the lead. She is the lead quantum ambassador for an organization called IBM. So you know this is serious. This is very serious. What is quantum? Well, a lot of us are still not quite sure, me included. So Kate has kindly set up a set of 4 events, of which this is the first, on quantum computing. And she'll be telling us more and more and sharing a lot of the skills that she's got and the knowledge of her super panelists to enlighten us about the world of quantum today. Of course, you may well be much more knowledgeable than I am about quantum. I hope you are, and that you will ask lots of questions. And if you're at home, likewise, that you'll put questions into the Q&A, the chat, and so on. We'll try and pick those up. And my colleague David, who is the secretary of Central London branch, will be monitoring those and feeding those questions also to Kate and the panel. Now, I mentioned the panel. I see only one other person here. She is obviously Rossy Nguyen, but she's not. Kate will tell us more about her 2 panelists, one of whom is here and one of whom isn't. Now, I know that's the principle of quantum as well. And in between and everywhere. So, Kate, would you be able to enlighten us some more about quantum computing and about your panelists?
Absolutely. Thank you, Darren. So I hope that everyone online can now see the slide that I'm sharing.
Yeah, we can see.
There's a slight delay. So welcome everyone to the first of, as Dallin mentioned, 4 sessions in a series of quantum computing deep dives, starting with the most basic question that I'm sure we'd all like to start with, which is what is quantum computing? I'm just going to run through a couple of points about how we're going to run this session, and then we'll dive into some prepared questions, but we will also have time at the end for audience questions and feedback, and David will be monitoring the chat as well for anyone sending in questions online. So today I've invited an absolutely brilliant couple of colleagues of mine that I've met whilst being part of this really exciting ecosystem and industry. And I'm really, really pleased to have both of them here. You can see a short intro to them on the screen. In fact, let me move this out. So first of all, we will start with some introductions, but as a general intro to how we're going to run this, we have 3 prepared questions, and for each of those questions, Adriana, Rossy Online, and myself will have a different perspective on the answer. And the reason I've done it like this is because it is my job to explain what is quantum computing in horrendous levels of detail that would send you to sleep within 5 minutes. But the way that I'd like to run this session is slightly differently. So Adriana works for a company called Karika, and she will introduce herself properly in a moment, but she's coming more from a recruitment background, and she's going to be bringing the perspective of a quantum workforce and what that means. Rossy Online works for a quantum software company that she'll tell us more about as well, and she will be bringing the perspective of what is quantum computing from the software perspective. And I work for IBM. IBM does a lot of things in the quantum industry, but most prominently it does build quantum hardware. So I will be representing IBM from the hardware perspective here. We will each try and answer the questions from a slightly different angle. So do forgive us if there's a tiny bit of overlap, but hopefully you will hear different things from each of us. So we'll each have a response to the 3 prepared questions, but then of course, if you have any questions at the end, do note them down and we will get round to those, and we do have time set aside to answer those. So let's get started and first kick off with some introductions. Adriana, if you'd like to go first with just an intro as to who you are, but also what's the company you run.
Sure. First of all, thank you, Darren and BCS for having me here. My name is Adriana Tan. I am the Recruitment and Relationship Manager for a company called Cureka. So Cureka means Quantum Resources and Career. So I think the name sort of explains itself when we're trying to sort of support the ecosystem in the area of resources, education, training, and career. So I'll touch more on that later on. Where I'll explain it a bit more about that.
Thank you, Adriana. Rossy online, if you can hear us, could you introduce yourself and also Riverlane?
Thanks, Kate. Hi, everyone. My name is Rossy Nguyen. I am a senior product manager here at Riverlane. At Riverlane, we are working and building an operating system for quantum computer. As you might know, that quantum computers to acquire new or time computing power. We are here building an embedded software layer for operating and operating these computers.
Perfect. Thank you, Rossy. And then finally, myself, I'm Kate Marshall. I work for IBM Quantum, and I have 2 different roles in IBM Quantum. First and foremost, I'm a developer for quantum applications and models, and I also work as the global lead for the technical Quantum Ambassador team. And the Ambassador team are a group of people that are basically charged with explaining the value, the impact, and what quantum means to various individuals, industries, and clients. So this is something I do a lot. As I mentioned, I've tried to shake it up a little bit here so that we have some different perspectives. As I'm sure if I brought you a physics lecture, you wouldn't all be here by the end of the hour. So hopefully you guys will all find out what is quantum computing from a slightly different perspective today. So we'll get started with our first question. So as I mentioned, we'll each have a go answering this, but the most obvious one to start with is, of course, in your own words, what is quantum computing and what does it mean to you? So I'll start with this one, and then I will hand over to Rossy online, and then so from my perspective, quantum computing is a new generation of information processing whereby we can take advantage of the fundamental principles of quantum mechanics, namely superposition and entanglement and other terms you may have heard of. Now, as I mentioned, I'm not going to spend the hour explaining what those terms mean, as again, you would be running out the door faster than I could finish the word entanglement. So what we are going to do is instead talk about what these terms bring to us. So basically, in one sentence for me, quantum computing is a way that we can harness these concepts, such as superposition and entanglement, to create environments or problem spaces that we can begin to explore problems that have previously been considered classically intractable. That's impossible to solve with even the most powerful classical supercomputers available to us today. There are a class of problems that we would consider classically intractable, and those are called NP-hard problems. And there's a subset of those problems that we would specifically iron out and say, these are problems that are really well suited to a different form of computation, one that's fundamentally different to anything we've been able to explore before. If you're interested, that subset of problems within NP-hard are called BQP problems. And they're the ones that we expect to one day be either solvable or prove much more efficient than current classical methods using some combination of classical and quantum computing or quantum computing alone. So for me, these problems that fall under this BQP category, they are few and far between, but it also happens that these same problems that fall into this BQP category are so important should we hope to maintain the health and well-being of our communities and build a sustainable relationship with our planet, that they really justify the pursuit of quantum computing. So what sorts of examples are these? They might include the development of improved nitrogen fixation processes for creating ammonia-based fertilizers. They might include the development of new catalysts to make carbon dioxide conversion into hydrocarbons more efficient and selective. They might be building better financial models to improve stability, predictability, and the growth of our world economies. or developing new classes of antibiotics to counter the emergence of multi-drug resistant bacterial strains. How are we doing this? Well, we're using a fundamentally different unit of computation, which is called the quantum bit or qubit, which obeys a completely different set of physical laws, the laws of probability rather than determinism, which is what we experience in our sort of everyday life. And I'm not going to sort of go into the details. We can have a separate session if there is an appetite for that on the technical details of what these things are doing under wraps. But really, these terms like superposition and entanglement, we can think of them as spooky quantum mechanical phenomena that present themselves or are observable when you're able to create conditions that are either microscopically small and or extremely cold. So there are lots of different modalities of how you can build these quantum bits. At IBM Quantum, we build something called superconducting qubits. And what you can see on the screen just now is one of our IBM Quantum System 1 machines. And the majority of that sort of gold mesh you can see is actually dilution refrigerator technology. And what that's able to do is to create a space at the very bottom of that sort of tube there where the quantum processor sits. And the dilution refrigerator is able to create an environment there that's closer to absolute zero than many other things you will ever find. It is one of the coldest places in our universe. It reaches 15 millikelvin, which is a huge engineering feat in itself that we can achieve those temperatures. So you can begin to understand the sort of technical and engineering challenges that are involved in building these machines. There are other ways to build quantum computers and to build quantum bits that make up these quantum computers. But one way that is approachable for this kind of technology is what IBM is doing to build general purpose quantum computers. IBM have chosen superconducting qubits that operate at these extremely cold temperatures in the fight for, I guess, general purpose quantum computing and generally useful quantum computing. The last thing I'll say is that what we hope to see in the future is a quantum processing unit may look like this, it may look slightly differently, it's difficult to tell at this time, but what we hope to see in the future is a way that will use quantum processing units in combination with central processing units and graphical processing units and all of the classical compute technology that we have today to work in tandem to solve the world's most complex problems like we have right now. So by no means would we ever expect to see classical computing rendered useless in the era of sort of quantum-centric supercomputing. They would always work in tandem and in harmony with one another. So that's the sort of hardware short answer to what is quantum computing. And I will hand over to Rossy for a similar perspective from software.
Thank you, Kate. So I'm just going to follow up with what Kate just said, that quantum computer in the future or now is hoped to work in tandem with classical computer. And if you ask me what quantum computer from software perspective, I would say quantum computer is not a next generation computer. It's a completely different way that we encode informations. So I recently came across a very interesting analogy about quantum computer that compare quantum computer and classical computer with a transport system. So if you think of classical computer as a bicycle and you have supercomputer, which is a car that can help you go further, do more computations, then quantum computer is not another type of land of transport, but it is a boat, for instance, that can help you navigate a different terrain and explore different type of problems. So here you can see on the screen is some picture of chemistry and material science. So when you think about quantum computer, I think more from the software perspective, you can first think of application layer or a lower layer, which is the layer that help to operate this computer. So at a higher level, the application level, you would have the layer where this application will be used running on quantum computer. So one of the promise of quantum computer is that being quantum system themselves, they represent other quantum system with much more ease and scale, much more polynomial in the system size. And this could make a huge difference in various different types of scientific research, but in particular when it comes to chemistry and material science. So as you might know that it's currently incredibly difficult to predict an exact property of battery material. You will need to describe the behavior of electron and the problem multiply every time you add one molecule. So with our current classical system, classical computer are really bad at represent these kind of mechanical system, quantum mechanical system. And quantum computer, since it's built and using the laws of quantum mechanics, is the best type of computing vehicle that we can use to measure these systems. But application in one side, currently quantum computer is currently under development. So we are building quantum computer, small scale, noisy quantum system. So now another side of software development is the software layer that actually used to operating the system. So if you go to the next slide, you will see that today quantum computer look a bit like this. So as a picture that Kate just showed, this is more illustration what is going in there. You will see there's a central computer which is operated within the fridge. It looking like a chandelier. And in order to operate this computer, you will have a layer of instruments like qubit in and out, or a local computer, an FPGA or classical computing device to operate these qubit at very cold temperatures. So it is a very complex system. And the current state of art, which actually a quantum computer built by IBM, is at 400 plus qubits. But however, we can only do 100 and plus operations before all this qubit decohere. So because before the computer become before it fail. So these kind of quantum computer is currently called in the era of the noisy intermediate scale quantum device, or short for NISQ. And so for exploring different algorithm on this small device has shown advantage, but at the same time has a certain limitations. So there's another parallel path of research to actually build the software that can error correct these noisy device. So in the next slide, you will see that an area of research is called quantum error corrections, which is using algorithmic software to protect different information that encoded into a qubit. And this branch of research, as I said, is the area that let's say the lower stack or layer stack software, which is used to build better and more stable quantum computers. So currently we're in a NISQ era, but in order to advance from this NISQ era, we need to solve two problems. The first problem is the scalability problem, which I think IBM spearheading in this field, because IBM currently have, I think, the biggest quantum computer exists of 40 plus qubits. The second problem is the second challenge is the challenge of operating this information in a coherent way and make sure that we can operate and run the circuit before the computer fail. So as the next slide, you can see that there's a certain, let's say, plot showing the next slide saying that let's say the mission of the lower layer stack of software is the quantum error correction, which can help us to unlock a higher value application, which beyond what the current NISQ device can provide. So a bit of long answer, what I'm trying to get to is that it's very exciting at the application level and from software perspective, but it also a lot of work, a lot of research going on the embedded layer of the software. Yeah.
Yeah, so now it's my turn. And so leading on to what they were both saying, who uses it, right? So financial industry, someone that's going to be one of the early adopters, manufacturing, engineering companies, energy companies. These are some of the people using it. And there was a report by McKinsey that came out last month that says that 4 industries likely to see the earliest economic impact from quantum computing are automotive, chemicals, financial services, and life science. What they think is that it's going to gain up to 1.3 trillion in value by 2035. And just to show you the slide that we have up at the moment, this is the worldwide quantum effort, money that's pumped in by the government of these countries. So the UK pumped in 2.5 billion, or they just announced that they're rolling out a new initiative of 2.5 billion over the next 10 years, on top of the 1 billion they've already put in the last 10 years, which brings it up to 3.5 billion. US, they have about 3.75 billion. So these are some of the bigger numbers. China, 15 billion, just to show you how serious everyone's taking it. Australia, India, South Africa. So this is up to date. What we have discovered so far, what our research is showing, and what they're estimating is that by 2027, it's going to reach 42.4 billion. So the European Commission as well in 2018 has agreed to put in 1 billion for this, and the United States House of Representatives passed a National Quantum Initiative Act as well. So everyone is having a lot of eyes on quantum at the moment. If you go to the next slide, just to give you an idea, these are some of the continents that are represented, and roughly how much everyone is sort of pumping into it. And if we go to the next slide, thank you. So roughly these, where are the quantum companies? These are the percentage of companies per country. As you can see, the tallest bar there is US. So the United States is leading it, followed by the UK, followed by bigger countries like Germany, France, so everyone is sort of, I wouldn't say a race, but everyone's taking it very seriously, and they're putting more initiative into it.
Excuse me, what about China?
Yes, so China too. China has pumped 15 billion.
Exactly, which is way more than the other numbers you told us.
Yes. Yeah, so that's what we know of to date. So now, the next question is, why is quantum computing important now? Yes. I think following all the slides that I previously showed that the governments are taking it so seriously, this was the one that I just, the 10-year vision that the UK government has just sort of announced, I think in April. It's about 61 pages. You can read it, it's online, where they're sort of planning to invest 2.5 billion over the next 10 years to sort of pump up the quantum technologies, not just computing, within the UK, I would say. So a lot of it, the last 1 billion has gone into R&D, putting in some money for postdocs and research, and setting up other institutes to sort of further the advancement of this study. And then this one, what they want, with this 2.5 billion, they're hoping to make the UK one of the world leading voices really in quantum. We are second after the US when it comes to place to go for investment. So what we also want to do is support the businesses, the local businesses around, and drive the adoption use of technology in the UK. So yeah, I think those are some of the key strengths. And now I think I'll pass to Rossy, who will take the second part of it.
Yes. So I think why is it quantum computing important now? We are all three of us are in the field, so we are very convinced. That's why we are giving a talk today. But I think from the software perspective, so I'm a developer myself, and I think in the next 10 years, right, when we said we will have actually useful quantum computing, 10 years, 20 years, but it will take a lot to actually building a useful application for this computer, to explore what is possible, and also to build the software to able to operate this computer. So why do we need it now? Because I think it takes not long term to actually build what we have today with Windows or the operations we had today. But at the same time, the application that we use classical computer today is also not something that we could think of 10 years or 50 years ago when we built the first, let's say, classical computer or a Mark II. So I think it is not the question of now, but of what to focus on. And from software perspective, I think there's a lot of interesting problems and challenges that need people to come up with and kind of help to solve. So that's my perspective on why quantum computing now. I'll pass on to Kate.
Sure. So we've kind of heard that quantum computation as a hardware and a software and as a workforce subject, it's extremely early in terms of research and development. And so it's quite easy to ask, and it's one of the most common questions coming from our clients is, why should I care today? Why does it matter to me now? And although we are at an early stage of research and development, we actually do have tools available to us today to start working with this technology, start exploring which problems we might want to use this technology for, and to start getting used to the paradigms and the new ways of thinking that this technology demands. So, for example, if we think about the fact that it may still be 5 to 10 years out before some sort of quantum advantage is demonstrated using these machines, but it takes at least that time to build workforces that are able to use these machines, understand the paradigms that I mentioned this technology would need from their workforce in order to use it. And realistically, we're already behind. It's one of the situations that is most common for me in talking to clients is to asking when they ask, what should I be doing today? It's getting people that are either from a data science or any sort of, to be honest, any background. This industry is going to need people from a breadth of backgrounds, but these people need to start getting used to this new technology today. Because once we reach this stage of quantum advantage, which is a point in time in where quantum computers can demonstrate a significant practical benefit over and above what any classical computer can deliver or demonstrate today, that's the point where we're already too late almost. We don't want to, at that point, be deciding, okay, now I'll learn about quantum computing and start getting to grips with the programming languages that you need to be used to in order to use these machines. It needs to come in advance to start getting used to this technology as it grows so that we can start understanding what the potential is and start maximizing the potential. So that's the sort of reminder as to why today we should start thinking about this era of computation for tomorrow. And we've got this slide on the screen and we haven't really talked about it yet. So what this is the IBM Quantum Development Roadmap. Now, this is a roadmap that touches on a lot of different things. At the very bottom, it's looking at hardware. And what we can see on this hardware roadmap is that in 2019, we developed a quantum computer that had 27 qubits. And last year, we created a quantum computer with a processor of over 400 qubits. So you can begin to see the scale at which we're progressing with these machines. So from a hardware perspective, this is incredibly exciting. However, I can't expect everyone in this room to lose sleep over the announcement of we've created a quantum processor with more than 1,000 quantum bits. So you could rightly ask, why should I care? And the reason that this is actually really exciting and interesting is that when we do release a quantum processor with more than 1,000 qubits, which is due to be released later this year, it means that the people that are mentioned in very, very small text, so I will read it out on the left-hand side here. So these software developers, such as kernel, algorithm, and model developers, when we release this hardware that's state of the art in terms of the world sphere that's looking at quantum computing, it means that kernel developers at the lowest level of that software stack can start using that quantum hardware to create low-level circuits with pulse-level control. And it then means that with those low-level circuits, the algorithm developers sitting above them can start using those circuits to create algorithms that exceed the capabilities of any classical algorithm available today. And with those exceptional algorithms, model developers at the very top of the stack start using those algorithms to deliver real value to real people by applying them to applications that can actually bring return on investment for companies or start to make real world impacts in the fields of drug discovery or well, I'm sure we'll have a question on use cases, so we can talk about that a bit later. But these model developers at the top of the stack can use the progress made further down in order to make real world impact. I'm going to answer questions at the end, but don't forget it. So that's obviously a roadmap such as this is really important to a company like IBM because it demonstrates that the rate of progress that we predicted some years ago now is being improved year on year. And in terms of hardware, we're absolutely a global leader in the space. And as Rossy mentioned, we have the largest computers available today, quantum computers available today. But it's also really important for the ecosystem as a whole because it shows us the path towards quantum advantage, or that point in time that I mentioned before, where we're able to deliver this practical benefit by quantum computers over and above what any classical computer can achieve. So this maps out the sort of future of what quantum advantage and quantum-centric supercomputing might look like. And you can see in the later stages, which really aren't so late anymore. I mean, 2023, we can start to link these different processors together. And that's going to be a really exciting time because that shows us how we might scale these machines to things like supercomputing and high performance data centers. And that's where things start to get really exciting. And that point in time is coming ever closer. So data such as this that IBM has been very confident in producing is actually hugely important for the whole ecosystem. I don't think I needed to say anything there. We'll stop there and move on to the last question that's prepared for us now, which is what does the future of look like for quantum? And Rossy, if you want to go first on this one.
So the future is very exciting. I think I have pictures of UK specifically. Startup ecosystem. So as you can see, what is shown here is the few, and I think this has been like since 2022, but now there's even more. But as you can see, there's a lot of different startup has placed their R&D, their labs in UK, and so you can see those, if you know that quantum computer is built based on different type of technologies, you can use superconducting like what IBM used to build their quantum computer, or you can use an ion trap technologies or co-atoms. So you can see on this map here, you can see, for instance, SICK use a unique inference SQ logic to build a quantum computer, or OQC, Oxford Quantum Computing, use a scalable Coxmore technology. So in general, in UK, I think is one of the country that has all the type of qubits research. So I think being as, working for a startup in the UK felt like this is the best place that you can work for and to develop and research and advance quantum computing industry. And I think what the futures look like for quantum computer, I would hope that we can keep working and building the ecosystem stronger. We can also have a better presence in the international market, because now it is indeed a race between many different countries and continents, given these technologies. But at the same time, it is very exciting for researchers and developers like myself to able to work with a different type of technology, very new and very weird at the same time. Yeah. I think I'd pass it on to Kate.
Adriana next.
Oh, yeah.
So that leads us back to how are we going to get ourselves ready for it? These are just some news headlines from around the world. This is, the next talent shortage. Everyone's fighting for talent. Everyone's talking like how we're going to build the next workforce. And I think there's another slide that shows that this was taken back from the New York Times, and they estimate that we will have that many jobs within the quantum industry, 58,000, 580,000 jobs, sorry, by 2040. So what we need to do is sort of get people, one, aware to like what's going on, get them ready, see who would be interested to pivot even though if you don't come from a quantum background, not many of us currently work well. I'm speaking for myself. I'm not a scientist. I don't come from a quantum background. But what I'm trying to say is we would need all sorts of people within this industry. So that leads me to my next slide. At Cureka, as I mentioned earlier, these are some of the things that we're doing. We provide training. All our training is CPD certified. So we try to bring things for everyone from very easy to understand, quantum for everyone, to very specific training tailored for industries or companies that want specific training done for their companies. We also do business consulting. So if your business want to see how you can take advantage of the new quantum technologies that's coming out, then we'll come in and, well, not me, but a team from the company will come in and see how they can work together with you on that. Quantum recruitment, that's what I mainly spend my time on. So within that, we work with companies who are looking for very specific talent and or looking to scale the companies, and also people who want to go into the industry. If you're thinking, how can I get involved? What can I do? Come speak with me, because we are looking for all sorts of people from very technical roles to very non-technical roles to commercial roles as well. So come speak with me on that. The other thing we also try to do is create awareness. So we do a lot of events, like quantum career events. We've been doing this for a few years. So the next event that we're launching will be Quantum Latino. We're the first to sort of bring an event within a quantum event to sort of bring together the Latin American market. So that's happening in Peru in October. So do join us in person or hybrid. We'll be bringing all sorts of people, from researchers to people working in industry to people who are just curious about quantum, sort of network and connect people and just see the ecosystem they thrive, really. And yeah, so that's just a bit of what I mentioned. We just recently launched this thing called Cureka Box on Quantum World Day, which was on the 14th of April. And what it is an interactive, hand-based sort of module that you can learn, and it's sort of targeted towards secondary school children, undergraduates, so they can learn it at that stage, because we want to start them, expose them early to quantum. So by the time they go to uni, or by the time they grow up, they're like, wow, this is a career option for me. This is something I can do. So we do a lot of things, like we've partnered with SpinQ, where they have a desktop quantum computer. So we do training companies who want to have experience with that as well. So with that, I'll pass it on to Kate. Thank you very much.
So yes, and what might the future look like from a sort of hardware perspective? Well, I sort of alluded earlier to the fact that we're not hoping to see sort of classical computers rendered useless. And in fact, our future vision is, I think, the sign that we have done our job correctly. And by we, I mean the whole ecosystem and the whole industry. So software companies, workforce companies, hardware companies alike. We will have done our job correctly when people that do not have a background in quantum physics or data science, or know everything there is to know and have a PhD in one of these associated subjects, the job will be done well when everyone can interact with quantum computing technology. And that will be a time where people can program sort of problems or experiments, and they'll be able to submit it to a system that will be able to divide up a problem into different workloads and assign those workloads to either a QPU, or so a quantum processing unit, or a CPU, a central processing unit, or a GPU, a graphical processing unit, depending on the type of problem. And you would not need to know about the underlying infrastructure and able to run that experiment, that sort of problem. And that is when we will have done our job properly, is when this technology is accessible to everyone. We are not at that stage yet. However, as you can hear, there's lots of research going on about how we might look to build that as a sort of an ecosystem of the future. And there are tools available today to upskill yourself in using them. I wouldn't be doing my job if I didn't mention that since 2016, IBM put more than 25 quantum computers on the cloud available for free. So you can log on to cloud.ibm.com and access our quantum page, where you can access any number of machines for free and start. We have an interactive user face where you can drag and drop sort of gates in a more interactive and visual way, if that's what you prefer, to start building quantum experiments. And there's also a Jupyter Lab or Python interface if you prefer coding your own problems. So absolutely, there's hardware available for you to use right now. There's software communities, so we've heard about a few of them. There's loads of things out there. One of the largest open source software communities in the world is IBM's Qiskit community. That's Qiskit. That is a Python-based software development kit for programming quantum computers, and that's what we use on our cloud-based interactive user interface as well. So there's absolutely ways that you can get involved now. What we hope to see in the future is this vision where there might be multitudes of different types of hardware, different types of software, and these layers will work together to be able to enable a whole community of people to use quantum compute technology. And in IBM language, that feature is called quantum serverless. And quantum serverless will be the point in time where people can submit jobs, and the sort of system or the serverless operating system will be able to assign those workloads to the respective type of processing unit, depending on the type of problem. So that's where we're sort of moving towards. That's the end goal, and we're making steps getting there. But what does the actual physical systems look like? Later this year, we're due to present our first prototype of IBM Quantum System 2, which looks very futuristic and cool. So I wouldn't be doing you justice if I didn't show you how this works. This is a modular system. So rather than that one tube you saw in the first picture, these are modular systems that scale and connect in multiple directions, so that you can start to imagine building a quantum computing sort of supercomputing data center of the future. So this is sort of vision that IBM have, sort of combining iconic sort of architecture and all of the lessons learned that we've made in building the largest computers to quantum computers to date. And it's culminating into this as one suggestion as to what quantum computing data centers might look like in the future. So very cool stuff to look at and very alien at this point. Now,
How long until it gets onto your desktop?
So I can access one from my desktop right now.
No, but how long until you get a quantum computer on your desktop?
Well, it's difficult because, for example, I mentioned.
I understand about the physical implications, but for me, I know it's a disruptive technology. But for me, how long until you think you can get a quantum computer on the desktop?
So I'll return to the point there about. So currently, IBM quantum computers are building superconducting quantum computers. That means that they need to be in fridges that reach temperatures of millikelvin. And if you were to have that on a desktop in front of you, you wouldn't have hands for very long.
No, I don't want that. I don't want that.
In that sense, you wouldn't necessarily need. However, from my perspective, one model that we're actually really pushing right now is that we have 25 computers that I said were freely available via the cloud right now. There is no need at this point in time for everyone to have an individual quantum computer available on their laptop right now or in their living room. We are going for basically pushing a model towards the idea that this is something that's actually very eco-friendly, in the sense that we wouldn't need an individual machine per user. You can imagine that sort of climate impact that would be extremely huge. And in fact, when you sort of measure up or compare the sort of classical computing data centers to what we envision a quantum computing data center, because obviously most of the energy that's invested into that system in the case of superconducting quantum computers is actually invested into the cooling system, that cooling doesn't scale with larger and larger processors. So although that initial energy investment made into making those super cold environments is extremely large, it doesn't scale with the larger and larger computers that you have sort of as you create a medium to large machine. So it's actually something that's really works in favor of quantum computation. And that's one model that I think is really important and actually really valuable for us at this point. That there is 25 computers serving a global community of more than 400,000 users. I don't see a point in time right now where we would need one on our laptop. If we would be looking at room temperature quantum computers that are very good at specific tasks, and you can read about them online. For example, photonic quantum computers do operate at room temperature. However, they're good at very specific problems. And IBM are looking to build general purpose quantum computers that are good at a wide range of problems. So they're slightly different goals. So I will just summarize and I'll hand over to David to introduce some of the questions. But as a summary, we've covered a few sort of introductory questions. We covered sort of what is quantum computing from a literal perspective. We've heard that it's a fundamentally different type of computation that uses a fundamentally different unit of computation called a quantum bit that behaves and obeys the laws of quantum mechanics, which are probabilistic. And I won't go into the maths of what that means. But what that gives us is the ability to create problem spaces. They're called Hilbert spaces, to explore problems that we've never been able to explore before. So these concepts such as superposition and entanglement, what they give us is actually an infinitely more complex problem space to start to explore problems. And I can give you some examples of that if that's something that you're interested in talking about in the question session. We also heard from the perspectives of software about the investment that's going into this ecosystem in order to enable users to start using quantum computing today. And we heard from the workforce perspective around the different sort of roles that are being built up to support such an ecosystem, but also the challenges and the investments that are being made across Europe and across the world into this industry. Next, we looked at sort of why is it important now? And we tried to stress the point is we are not at an age where we're beyond these noisy intermediate scale quantum machines that Rossy mentioned, but we are at a stage where we can start to prepare ourselves today for an era of computation for tomorrow. So I really do encourage you all to look at all of these tools and get to grips with actually playing with these machines today, because, well, why not? It's something that's definitely going to be here in the future, and that we do have the tools available to us today to become quantum ready, as we're calling it. We also heard again about the need for building software that can offer error-corrected results, which make them more accurate and more usable, so that we can actually make these noisy quantum machines more useful today. And finally, we also spoke about what the future might look like, and we looked at the sort of literal futuristic images that IBM Quantum are going to start building this year, and then furthermore year on year. But we also looked at what the software stack might look like in the future, and the different things we need to build to support these machines, such as operating systems, compilers, and various different pieces that go together to enable a user community. And we also looked at the different roles and what sort of workforce would be needed to support this. And that goes just well beyond just technical roles. In the organization I work in, we have product owners, we have business analysts, we have every sort of job that you can imagine in any technical workforce today. We will need people like that in the quantum industry that are able to understand and communicate the impact of quantum. So by no means do not be scared of the quantum industry if you do not come from a physics or a strictly scientific background. We will need people from industry angles to identify the use cases. We'll need people from design angles to understand how these things should look like. And we will need people from every part of the sort of workforce that we have today. So hopefully that's started getting your minds ready for the questions. I don't know whether, David, you want to read them out from there, or?
Yeah, I can do some of the online questions now. We've got a question for Kate from Peter. Can you provide any more information on the IBM 100,000 qubit project, error corrected or not, and what quantum algorithms or problems could be performed on such a platform, and what would not be feasible?
Sure. So the 100,000 qubit challenge that's been released, I think it was the press release for it came out in the last sort of 48 hours, is basically a challenge where IBM is partnering with global universities, the University of Tokyo, I've now forgotten the second one, which is terrible, but I think it's the University of Chicago. I hope I got that right. And with these two universities, we're basically trying to look at we're committing to build a 100,000 qubit quantum computer, and I've forgotten the year off the top of my head, but I think it's 2032. So that is realistically not very far away. We mentioned before this era of noisy intermediate scale quantum computation, and I think it's easy to try and imagine that there's going to be 3 different phases of quantum computation. We're in this first phase of noisy intermediate scale quantum computation, which is when these machines are extremely immature. The research that we're doing with them is really exciting, but it's not demonstrable. Nothing we can do with one of these computers today would be completely impossible to do on a classical computer. We haven't got to that stage yet. There's lots of problems that we're looking at where we can see speed up and we can see improvements made on energy efficiency or on sort of smaller scale wins, but there's no demonstrable impact that would be completely impossible to do on a classical computer within any reasonable amount of time. When we hit that point, we will move to an age called quantum advantage, which is where we're able to demonstrate capabilities over and above what classical computers can do. But beyond that, still, there's another era, which is called fault tolerance. And fault tolerance is when we have this universally useful quantum computer, probably multiple of them, that are able to solve a wide range of problems, and far more of them than we can probably think about today, because again, as we mentioned, people are still going through that phase of problem mapping and use case development. So we're not even aware today of all the problems we might use quantum computing for in the future. this 100,000 qubit quantum challenge that we're working with universities to try and build machines like this will hopefully mean that we move into the next stage of quantum advantage, but maybe even further, and may help us to move towards that era of fault tolerance that we can see as the far future, but will be a very exciting time.
I want to go back to the question I had before, but actually just using your model of the 3 phases. Do you think the architecture stack will shift in those 3 phases? Because it sounds to me like, and correct me if I'm wrong, you currently need to have a classical computer to interface back into, a bit like the question there, you need your device in front of you in order to get to the cloud, in order to access it. But actually, it sounds like you probably need some kind of GUI interface that sits on a classical machine that then allows you to go through. And I'm really interested in 2 questions. One is that what's missing off your stack diagram that you gave us, because the classical machine needs to do. And then this thing about the phases, do you think it will shift so that we have a full quantum stack by phase 3?
So I definitely think, regarding your point there, it's extremely important to remember that we use classical computers to interface with these machines. We use classical computers to design the problems we want the computers to solve. We use classical computers to read the results. Classical computers are absolutely essential to this ecosystem that we're building. And I don't see that ever changing. I don't think there's ever going to be a point in time where we won't interface with these machines using classical compute technology. I think that's just because when we think about quantum computation, remember, it's a different way to solve problems that are intractable today. Interactivity with computers is not one of those problems. So I think it's not something that would be applicable to. I can't imagine a world where we wouldn't have that as our interface.
We're not going to an era of like a Xerox PARC again, where we have to figure out how to interface with these devices.
I mean, these are all conjectures at this point, but
yeah.
I do not think so.
Okay.
Regarding what's missing from like this roadmap that we looked at, that's difficult to say. Obviously, this is just an idea of what we think is coming and what we think we should expect. But this is extremely exciting. I mean, the engineering challenges to get to something like Kookaburra over there in 2025, we haven't even begun to broach the subject of how you might connect those machines. We're only this year going to be creating a series of quantum processors that are connected by these interconnects. And these different interconnects will be hugely difficult from an engineering perspective, never mind the sort of science that's outside of that as well. So yeah, it's difficult to say what's missing, but this is just an idea of what things may look like. I think you then said would the architecture change? Again, I'm not sure. I think like one of the big questions today that I was discussing with Dalam the other day is how might we look at bridging the gap between high performance computing and QPUs. That is a huge open question in terms of when you're looking at the future of quantum centric supercomputing. Would you have QPUs on site in a high performance data center? Or would you have them remote and connecting over the cloud? What does that mean for latency? And does that mean that the problems you're trying to address with high performance compute is then not worth doing because you're trying to connect through sort of cloud-based connections? Does that mean you then need to build sort of an environment that can harness super cold temperatures to temperatures of absolute zero? These are questions that will appear by the day as people start to uptake this technology. So it's very difficult to say, will the architecture change? But really, really good question.
Yeah, so it sounds to me like my takeaway is it's like the low level architecture from my perspective, thinking a bit interface perspective, is actually the things that are continually going to change all the way through. But it sounds like that tier above it, with the what you call the algorithmic developers tier, actually is the skill set that you were talking about is worth developing now and interfacing in, because that will stay quite similar.
Yeah.
Thank you so much.
No worries. David, is there a question for Rossy or Adriana? Because I've done a lot of talking.
We've got a question from Olu. When will companies need to be concerned about quantum computers breaking current encryption?
Would you like to
Rossy, like to take that?
Well,
it's $1 million questions, yeah. Maybe I'm going to put something in perspective. So I think now we're looking at the roadmap right now. We see 4,000 plus qubits, physical qubits. And I think Shor algorithm, one paper estimated that you need 20 million qubits to run that algorithms. Of course, you can say that we don't have to worry about it, but challenge with scaling quantum computing is not by multiply number of qubit counts, but rather how do you put the two chips together and you can double the size, and how do you put like a series of like 10 chips together. So I don't have the exact years, but I think it can be as soon as we solve some of the critical challenge of scaling quantum computer. So.
Yeah, I think the cryptography question is really important, because obviously that's, I mean, cryptography as we know it today is, it's a whole area that's based on the fact that the factorization of large numbers is NP hard. So as soon as we have a machine that's able to solve a subset of NP hard problems, and the NP hard problem that's relevant to cryptography lies in that subspace of NP hard, which is relevant to quantum computers, we're in trouble. That is something that is recognized throughout the industry. It's also something that people have started to mitigate against today. There's a lot of hype around this scare, and it's something that obviously it's really important to talk about, but it's also important to remember that last year, the National Institute of Science and Technologies in the US released 4 different algorithms that were quantum-resistant cryptography algorithms. And these are 4 different algorithms that can be used in different sort of mainframes or whatever system it is you're trying to encrypt. There are steps you can take today to protect against your against sort of quantum attacks, as it were. These are things that are recognized, spoken about, and are able to be mitigated against. So although it's really interesting to encourage people to think about when breaking cryptography might happen, it's also really important to remember that there's things companies can do today to protect their data. We don't, it's difficult to focus purely on when this becomes a threat, because for me, it's a threat today. A malicious user could steal your data now and keep it in their home for 10 years or 20 years, until which time we have computational technology that's able to decrypt that and use it maliciously. So for me, it's more important to think about what can we do today to protect ourselves, rather than trying to predict the threat, because the threat exists for me right now. So I would definitely look at that in terms of what can we do to mitigate against it, and there are ways that we can do that. And people have done that already. And those different cryptographic methods are based on problems that are too hard for a quantum computer to solve, which there do exist, those problems. Yeah.
Hi, I'm an ergonomist, so I'm interested in the intersection between quantum computing, ethics, and artificial intelligence, because you've just illuminated the fact that we're going to need all of these new skills. But if AI is currently capable of writing software, why would it not be capable of developing this and producing its own roadmap and producing its own development plans and producing its own stuff? In other words, why would it need us?
Yeah, it's a very big question, isn't it? It's very tricky, isn't it?
I only ask big questions.
No, very good question. I think for me, the way to think about that is that there are things that obviously, with things like ChatGPT, it's very quickly easy to see how people's jobs might be rendered slightly difficult to justify when a computer can develop things. But this is such a new technology that we have no data to train against to build something that would be able to cope with this sort of technical stack that we're all learning as we go. And I would say for me, at least, it's not something I would be scared of, from the sense of this is something that we just can't prepare for in a way that you could train a model to, I guess, to build it for you. This is something that we're learning every time we build a processor and add one other qubit. There's technical challenges that go with that we would never have predicted. And it's definitely something that I think, it's difficult to simulate what quantum mechanics will introduce for us in terms of engineering challenges of the future. I think AI and the technology that we have available today will certainly help in terms of trying to resolve those challenges. But I wouldn't say there's a threat of AI being able to build this software stack instead of us, because I just think there's so many unknowns to the point of what would we be training that on, and there's such little data to work with as it is.
And you'll be happy to know that part of the 10-year plan, they are sort of talking about coming up frameworks on ethics and how do you navigate things like this, not just within the UK, but I think Spain sort of mentioned it too when they came out with the paper. So a lot of countries are aware that this is important, so they are looking into talking about it.
It will be used unethically anyway. That's a
Yeah.
given. So, you know, the ethics around it, that will, yeah, it will be misused.
Yeah, I feel both excited and intriguing about the potential of quantum. I'm looking in the future, the potential of quantum. For example, you cite about drug discovery and very complex model. So now 2023, do we have any like case studies that some drug companies have successfully used the quantum computing to discover some drugs treating some illnesses?
So if they had, you would have heard about it. So absolutely, that's sort of one of the use cases that's extremely exciting for quantum computing. It's not something that's been done so far. That would absolutely be some sort of demonstration of quantum advantage if we weren't able to discover that that chemical or that antibiotic resistant strain without classical compute technology. But it's absolutely the sort of area that will be really exciting to look at. Quantum computing is useful for 3 different types of problems, namely simulation, optimization, and machine learning problems. All of the problems that we're looking at today fall into those 3 categories. And in terms of chemical simulation, simulation of nature is incredibly difficult as it is. When you start to consider that nature is by its definition quantum mechanical, it makes sense that you will need a quantum mechanical machine that is able to simulate the behavior of that. So there are already problems that we're looking at today where we can start to look at the low level behavior of chemical interactions and sort of energy levels of chemical structures that we've never been able to really understand before. Rossy mentioned sort of lithium oxide and lithium ion batteries. We're starting to understand batteries beyond what's been capable today. And that's not a demonstration of quantum advantage in the sense that you could probably do that simulation experiment on a classical computer and it would cost you 10 times or X times more sort of compute capacity to do so. But with this new compute technology, new different type of compute technology, we are actually able to start exploring the low-level behavior of chemicals in a way that we've never done so before. So absolutely, drug discovery is a key area. You may have seen online the Cleveland Clinic in the States is is the first center to have purchased an on-site machine that will specifically be looking at life science applications. So that's a gesture towards what we expect to see in the medical field and in the life sciences field. The investment that Cleveland Clinic are making, that is towards end goals such as drug discovery. So absolutely, that's an area that will be exciting. Is there another question online for?
Yes, we've got one last question from Rabina. He's a master's student, and do you have any advice on jobs or internships in the quantum industry?
Hi, absolutely. If you look at our website, Cureka, we've got lots of resources, including internship, quantum companies, or connect with me, and then we can chat about this.
What's a job offer now?
Why not us?
Thank you for the talks. It's really been fascinating. I'm wondering, given that there seems to be alternative technologies around to implement quantum, why did IBM choose this super cold technology?
Oh. We get all the time.
So obviously we mentioned there's various different modalities. IBM are doing a very specific task, which is they're trying to build general purpose quantum computers. There's only a couple of the various different types of modalities which prove to be even slightly maybe successful at doing that task. And superconducting sort of transmon qubits, as they're called. This is one type of probably only 2 that will have been suggested to be useful for general purpose machines. So when you sort of restrict the choices down to the 2, then IBM has a very long history of sort of superconducting material development, and all of the material that goes into one of these quantum processors, the materials that you're aware of, it's silicon. It's the actual physical type of qubit that we're using is using a Josephson junction. This is something that IBM has been developing for a very long time. So probably the decision there between maybe the 1 or 2 options that were available to IBM in the goal of producing general purpose quantum machines, it probably goes down to the fact that we are one of the best manufacturers of processors, and we have a very long history of that. So that's probably meant that we lent that way. And to give you sort of a suggestion of what other people are doing, Google is one example of a company that's also trying to build general purpose quantum computing machines, and they were also using superconducting supercooled qubits. So it's a suggested way that we hope to see in the future. However, in an ecosystem like this, any progress made on any type of quantum technology or quantum computing modality is a success for everyone. IBM is one company that's building hardware, but we're also building a lot of software, because regardless of what type of hardware proves to be the most successful, you're going to need software to run it. You're going to need operating systems and like everything that Rossy described in order to interact with it. And maybe one day we'll see a future where there's lots of different types of quantum computers being used for different tasks. That sort of, the questions are endless, but yeah, really good one. Thank you. At the back.
I don't know if it might be up there, but I just can't see. But what's the magic number in terms of number of qubits, and how far away do you think we are from that?
Rossy, do you want to answer that one?
Magic number. Oof.
Deal number.
Just gonna give you numbers. So I mentioned, I think for encryption, the short algorithm used to break encryptions, it required 20 million qubits. But if you think about physical qubit, it's quite noisy. You need to protect them. So you have a ratio of 1 logical qubit, which is protected qubit, to 20 physical qubit minimum. So yeah, that arrives at around 200 trillion, a million qubits.
Think of
400.
So 10 years away?
Yes, hopefully. Yeah.
I think one thing that's key for the client discussions I have is when we demonstrate quantum advantage with one use case, that does not mean we have a computer that's able to do everything. That will be far in the fault tolerant stage, where we have generally useful quantum computers that are commercially available and useful in lots of different settings. So that will probably be the point in time which you're referring to. Lots of other people are sort of asking, how many qubits would we need to make to reach quantum advantage? Again, that's sort of, you'd be licking your finger and holding it in the air with any answer you gave, but there is a suggestion that it should be in the next 5 to 10 years. And I would be very, very surprised if it took longer than that. I'm definitely hoping to see it in far fewer. Yeah.
Has IBM looked into carbon-based organic room temperature quantum computing?
IBM doesn't. They only look at supercooled superconducting trans-1 qubits. However,
there are obvious advantages.
Of room temperature ones or of supercooled ones?
Yes, of room temperature.
Well, obviously, because you wouldn't need the infrastructure to support the near 0 Kelvin temperatures, that's a clear advantage. But those quantum computers do tend to be very good at specific tasks rather than generally useful. So it depends what sort of, like, if you're a startup, what your goal is. But room temperature quantum computers are a task in themselves, but they're generally seen to be not generally useful. So they're not general purpose. They're very good at, for example, optimization tasks, but they might not be so good at others. So it depends what your goal is, but obviously room temperature quantum computers are very exciting in their own right. They're just trying to do a different thing.
Sorry, follow up with what I asked before about when you get it onto your desktop. I mean, it was a serious question. I like visionary things. My understanding with regards to quantum computing, particularly the model that IBM uses, is that it does use a lot of energy.
Could you speak up a bit?
And we have global issues with regards to data centers and the amount of energy that they use. And in some countries like Ireland, I've heard reports that maybe up to 20% of their energy is being used for data centers. A quantum computing data center, does IBM have any numbers? And I understand why you're going down this route, because it does support your long-term business model. Everyone said the mainframe was dead a few years ago. Now it's back again. Data center on the cloud. Do you have any numbers to say how much more energy quantum data center will use than a normal massive parallelized data center?
So I wouldn't be able to tell you any numbers, partly because we just don't have anything.
But do you think from the gut that it would use a lot more energy to maintain that isolation? Because I understand even atoms coming through the barriers can cause problems. And you also have issues about storing information as well. That has now been resolved.
Yeah, no, definitely.
Has that been resolved now, or is that still being worked on?
Information storage is incredibly difficult. So I'd go back to what I mentioned before, just around when you have one of these things called fridges, and the fridge that I showed you right at the beginning of the presentation, the system 1, that held our 27 qubit machine, that held our 65 qubit machine, it held our 127 qubit machine, and it's now currently hosting our 433 qubit machine. Most of the energy that goes into the GPU that we see today is going into that, generating the super cold temperatures. However, that energy has not scaled from 27 to 433 qubits. So from the data that we have available today, it would suggest that quantum computing will be quite favorably seen in terms of an energy cost perspective, purely because it doesn't scale in the same way that a classical computational data center would scale when you create a much larger FPGA or whatever you're looking at. So from that perspective, it would suggest it's actually quite favorable in the argument of.
So you could cut down on energy usage. That's what you're saying.
Yeah, if your fridge is able to host larger and larger chips, which we're able to do. It's not able to host 1,000 ones. That's why we're bringing out system 2 to host the 1,000.
And there's just one question, because I remember a couple of years ago there was a wonderful series on TV called Devs, where someone built a quantum computer that could project the future and the past and everything else. Brilliant sci-fi. I advise everyone here to watch it. It's a wonderful series. But the question I wanted to ask is, with regards to a real world problem now, has a quantum computer come up with something which has been verified as being correct?
Yes, so everything that we can do today is verifiably correct. It's actually it's going to be a really large problem for us when we find something that's a classical computer cannot do, because how do you verify that? So that's going to be a huge difficulty, and it's one of the reasons that we're looking at HPC solutions for verifying these things, or simulators that can maybe verify results. But for example, I mean, just drawing on the example that Rossy mentioned in her slide, the development of lithium oxide batteries, we do some work with Mitsubishi Chemical to basically simulate the low-level interaction between oxygen. And so one sort of commonly known issue with lithium oxide batteries in the battery development world is that you can accidentally create lithium peroxide, which is an undesirable molecule in the sort of efficient behavior of a battery operation, when you're actually trying to create lithium dioxide. So if you create lithium peroxide, it's harmful, and if you create lithium dioxide, it's great. What we're looking at with Mitsubishi Chemical is ways that you can use some additive chemical to prevent the synthesis of lithium peroxide. That is something that we've never been able to do with a classical computer, and it's never been justifiable from a sort of computational expense perspective. So that's a verifiable calculation that we've been able to do with quantum computers that's actually been really helpful in the field of battery development today. It wouldn't be a demonstration of quantum advantage because you could do that simulation experiment on a classical computer. It would just cost you a lot more and take you a lot more time. So it's not impossible to do, but that's one example of a verifiable calculation.
There's a benefit there with the time and the cost that you just said there. Thank you.
One simple question. A company in Canada called D-Wave, I hope you understand, they are using different quantum technology, quantum annealing technology. In terms of the qubit, they are more advanced than IBM, I think, more than 100 qubit years before. So how do you compare these two companies or these two technologies?
Rossy, do you want to answer that one?
Yeah, sure. I can give you a quick answer, but I think it's about D-Wave and IBM. So, Kate, I think you're a better person. But I think, yeah, so I think IBM, as Kate said, is building a general quantum computer, so universal quantum computer, while D-Wave is building annealer. So the annealer quantum computer is to solve a very specific problem. So I guess you can't really count number of at least we in the field, we don't look at the qubit count between these two different type of machines. We see what problem it can solve. Yeah, that would be my thought on it.
Yeah, quantum annealing is not quantum computing. It's different technologies. It's hard to compare. They can perform similar tasks in that quantum annealers are very good at solving optimization problems. Quantum computers are also good at solving optimization problems, but that's the only overlap. So it's difficult to, like, they're just, again, they're trying to do different things. Quantum annealing is a very promising technology for solving optimization problems, and there's been really exciting research in the field. It's not quantum computing.
Adriana,
Do we have time for more questions? We do.
Adriana, you showed the world map. You said very specifically it's not a race, but at this early stage of the industry, is there a lot of collaboration between countries, between industry and academia? Is a lot of the research very open, or is there a lot of intellectual property and trade secrets and cloak and dagger stuff going on? What's the overall climate like?
On a high level, I'm sure there's some sort of, with some countries, they don't really talk to each other, let's just say. But generally, it's a very collaborative community, which is what I love about it. And you need to, because we're so new, so we need to sort of support each other. So there's a lot of, collaboration between academia, industry, people who are, just, there's a lot of collaboration going on, sharing what they're doing, conferences, people sort of sharing what they're doing, updates. Of course, I'm sure some companies don't share everything, right? It's just that they're still quite open about it.
Is it possible to give some more examples of successful experiments?
Yeah, sure. One each. I don't know. So, for example, one of the most commonly referenced is, Adriana mentioned earlier that the financial services sector was one of the early movers in this industry, partly because they have a lot of money, so they can invest in research and development. So one of our kind of, I guess, most prominent partners is JP Morgan Chase & Co. They did an experiment nearly 4 years ago now, which was basically proving quadratic speed up in portfolio optimization techniques. So they were able to drastically reduce the time taken in estimating an optimal portfolio so that they could turn options into prices and products for customers. That is another example of where a quantum algorithm has proved extremely successful at a task that we otherwise have used classical computing for. Again, that is not a problem that's classically intractable. It's something that just costs more energy when you do it with classical computers. That's another example of something that quantum computers have demonstrated they're good at. And obviously, I guess if you're an investment firm, that gives you an edge because you can come up with the same answer at a much lower cost in terms of time and energy. So that's another example of a use case where quantum is really, really successful. Rossy, do you have another answer to that one?
No, I think for finance, yes, but I think in also another example is for pharma industry. So there's a lot of research been done in, let's say, how do I make it less technical? So I think it's like when you run an algorithm, you will have a certain part of optimization that you can actually make use of the way quantum computer encode informations, and one of them is quantum phase estimations. And so now there's been a lot of research into using quantum phase estimations to explore a new type of drugs. That's also a very interesting use case.
Thank you.
Well, there's one automotive company that sort of use design modeling powered by quantum to sort of create more aerodynamics in what they're doing, cost reduction, supply chain, as well as what they're looking at.
Okay.
Okay, one more, last one.
A question about sort of quantum familiarization. Is anybody looking at sort of gameplay based on quantum effects so that people can build up a familiarity with the bizarreness of quantum mechanics through gameplay, bring that into the sort of the youth market or whatever?
Yeah, actually there's a lot of things being developed at the moment, like our Cureka box it's a very interactive thing. It's a physical qubit, and there's a lot of.
I mean, actually playing a sort of a game where the principles of the game are governed by quantum mechanical ideas, so that you get into thinking of the weirdness of quantum mechanics without having to sort of understand the maths of it, and the mental reflexes that then you carry through when you get into actually trying to study, use or exploit quantum mechanics. Anybody doing that?
To me, that what I can say from what we just launched is very interactive. It's again very playful. They do the spookiness and the movement of the qubits, and talk about Dirac notation and all that. So it's just very basic level, but it breaks it down quite simply. It's quite interactive. So
maybe watch that series Devs and see if you can find any nuggets.
I think there are some people probably developing, or there's probably something out there.
I've seen something called quantum chess.
Mm. Different people are doing different things, so I'm sure there's probably something out there. But there's always room for more products. So.
Yeah. Just one final one, if I may.
Final short question.
Sorry, you talked about collaboration. It's probably is China collaborating with the rest of the world?
I don't know much about the Chinese economy.
Not sure, honestly. I think that's a very tricky one. Yeah.
They're already way ahead. They're already way ahead.
Quick one. No, sorry. We talk later in the break. Yeah. Great. Yeah, thank you very much, the three of you, including Rossy. That's been really fascinating. But I'd like to spend just a few minutes casting some more ideas your way. We are in an age and in a profession where the boundaries are just expanding all the time. The multidimensional aspects are becoming very much more multidimensional. The SDGs, the Sustainable Development Goals that are set for the 2020s by the United Nations and others are aiming to unlock tech for these. We are aiming to unlock tech for those global goals. And just to put into perspective some of the things that have been said here about quantum, where is it going and so on. We're in a world where we are pushing the boundaries on blockchain, IoT, big data, advanced materials, robotics, AR, VR, alias now metaverse, 3D printing, drones, 5G, synthetic biology, cloud, internet access, and something called AI. Well, what does that mean? The honest answer is we don't know, because it's advancing day by day. But I will say that this brilliant series that's being conceptualized by Kate, this is the first session that you've just seen, but the other ones are what does it mean to be quantum safe? And that will come in July. In October, we'll have the quantum computing industry in the UK, and I can see there's a huge number of questions around that at the moment. And then in December, are we ready for quantum advantage? Well, we certainly don't seem to be right now. Will we be by December? I wonder. But setting the scene again in terms of what we are doing here in the BCS and in our BCS London groups, we have got a number of initiatives. I've just described one in some detail, which is the one that Kate's leading on quantum. We have another one on, guess what, AI. It's being pushed along by ChatGPT and GPT-4 and all the rest of it. So that's almost becoming a subset of AI right now, as you can imagine. What is possible with AI? Well, let's give an answer today, and then we'll have to change it tomorrow. We're going to launch a series on that very soon, in fact, on May the 31st. But the other things that we're doing, and this is in our three branches, the Central, North and South London branches, we have a community. You've seen some evidence of it here. Other colleagues of mine are at the back. There's Anna, there's David, who's doing the technical aspects of this session, and we'll parcel it up into a video that you can watch later. But the other initiatives we've got, I've mentioned quantum, I've mentioned AI. We also have a business analysis initiative led by Kitty, who's sitting in the audience there. We have a cloud initiative, and you'll see the next in the cloud initiative series tomorrow here, if you wish. So that is going to be on microservices and hybrid cloud applications. Then we've got a cyber initiative, and we've had a recent event on that, but we've got loads more to come, as you can imagine, with cyber. Will cyber hit quantum? Will quantum hit cyber, etc.? Lots of questions like that. We have an eco initiative led by Santana, who's in our audience here. And that has a whole lot more topics to run than we've done so far. We've made it on waste and how to stop it, but there's so many other aspects of eco, sustainability, etc., etc. Then we have a higher education initiative. We have an innovation hubs initiative, because there are innovation hubs. Are there 10, 15, 20? We stopped the list at 40 within the London region. And we're reaching out to them and asking them what they're doing, learning more. And you can bet your boots that a number of them will be working on some of these other areas and will benefit from their skills and their people at a later date. We also have other things, such as we have a recruit initiative. No prize for guessing what that might be about. We have a secure IT initiative, i.e. security other than cyber. We have a seniors initiative for people like me who are dangerously in need of falling over, dangerously in need of a stick, unless I fall over. And at the opposite end of the scale, we're going to launch an early careers initiative. And also underlying all of this, we have another initiative, which is called Womenspiration. And we will have events coming up very soon in May, at the end of May and in June on Womenspiration. The tagline is inspiring women with inspiration for everyone. But you too are an inspirational person. And we look for the ideas of people who want to join us and be active. And we give you the platform and the chance to tell us more, to learn more, and to benefit from each other's knowledge. Now, all of this we try to make into 5-star events. And Anna, who's at the back of the room there, is in charge of our event success initiative. So Anna, are you going to give out cards to somebody? Yeah, you are. Good. She's got some cards and she's going to give them to you and ask you for a score. Was this a 5-star event? Is my question to you. You can reply as you like, but what I'd like on these cards is one is how many stars you think this is. And we've got 6. That's fine. But also your comment. Give us 2 or 3 words, your comment about this. We will analyze those and to see how we can do better things. Because this is the BCS and this is for you. So that's the event we're running. We also have something else for you. David, do we have something else for you?
Yeah, we've got pizza and drinks.
Fantastic.
That's 5 stars.
Should
10 stars. Yeah, 10 stars.
I should warn you that Anna's handing these out. We would like some buttons. The pizza and drinks. How's that? Yeah.
Just anything.